Thank you and good morning. It's great to talk to such a crowd of distinguished scientists and technologists. Let's start with a story. Think of investing in a piece of real estate in Silicon Valley or around San Francisco about 30 years ago, or a mutual fund. It would have been almost 100x value today because Silicon Valley is not just hot market of technology, but also real estate. But the cost of creating a unit area of silicon today is pretty much the same as what it used to be 30 years ago. And it's amazing that maybe that's the only technology or the only commodity to really manage to counter inflation and offer such an opportunity for us to utilize the technology all over the place. There have been many different exponential trends in technology that really facilitated this success. Now, the advantage of having a vague title for your talk is that you can adjust the content until last minute without violating the title. But really, we are fascinated by exponential. That 1.1 or 1.2 to the power of 20 or 30 ends up being really a huge number beyond our imagination. What I'm trying to say today, and the main part of my talk would be that in the future, we see a different approach and different set of trends in semiconductor and different market trends as well, which is really exciting. For last several decades, our field has been dominated by mainly one trend, CMOS scaling, and exponentially getting more affordable, more dense, and lower power. And we all benefited from that immensely. But no exponential is there forever. And obviously, as you can see in this ITRS latest graph, we are getting really to the point of running out of steam. I'm not going to argue which node exactly is the node that the trend stops. But somewhere below 28 nanometer, we see that the benefit of scaling starts becoming less. And the challenges we are going to face are going to be also more in terms of design cost and complexity. Also on the market side, as Cliff showed in his slides, we have been used to relying on a single market and application to drive the next big peak in semiconductor. PC was a big driver, and then connected PC, internet PC, was the next driver that really defined the next peak. And the most recent one was the mobile. Amazing growth. But in the future, most likely that's not going to be the case for one technology. We are used to that, so we are searching for one market. IoT is going to be the next big thing. But the numbers don't show that it's going to be only one technology and one market defining the next peak. Most likely, multiple markets and multiple technologies creates this growth. Everything around us getting smarter. Everything around us is getting more connected. And that's the beauty of our technology moving forward. In 2015, we manufactured almost 800 billion semiconductor devices, almost about 100 pieces of semiconductor for every individual on the face of the earth, which really outgrows the number of people and the GDP, which is kind of tightly coupled to semiconductor industry. And that means the wave of electrification or electronification, if there is such a word, is getting faster, and it's even in the future is going to be even more diverse and exciting. Here's an interesting observation in automotive industry. These days, as you know, the value of a car is mostly defined by the amount of electronics. About 30% of the value of the car comes from the electronics inside the car. And this chart for me was kind of interesting to highlight the fact that the ratio of the growth of semiconductor content compared to electronic content, compared to auto growth content is 3-to-1. Means that every generation is going to have a lot more electronics and differentiate by the advances in semiconductor. I'll get to that later in my talk. Another interesting observation is the energy and the green challenges that we are facing. Power, as we get to higher voltage, tend to use less of the semiconductor, but that is changing. You're hearing about advances like solid-state transformers. You hear about the generation using more silicon, distribution using more power devices, and consumption optimization by using smart power. So this chart shows that without intervention of the semiconductor industry, the red line is showing the growth of the energy consumption. It's just for the United States. And with the intervention of the silicon, you can potentially save about 4,000 billion kilowatt hours. That's 4 trillion kilowatt hours just in US, and the same phenomena in Europe and Asia and elsewhere. So you can see the bringing intelligence at generation, distribution, and consumption can make a huge difference in terms of the efficiency of overall system. Same phenomena we see with medical. Medical has been a kind of a slower market because of the regulations around that. But we see the concept of personal medicine after many years are becoming reality. When I talk about personal medicine, I'm not just talking about recreational aspect of it, but also clinical quality, medical monitoring systems, which I'm going to talk about also later. So obviously we see the trend upward is not dominated by single market, because now almost everybody has a mobile in his phone. It's going to grow, but how many more mobiles can you carry in your pockets? So obviously we see the growth, we see the opportunities, but it's going to be highly multidimensional, both on the technology side and as well as the application and market side. So what is the magic of anti-inflationary technology? Maybe economists and politicians are envying the fact that you couldn't do the same thing on any other field by semiconductor. Let's put some basic numbers together. The cost of making a fab, a manufacturing facilities for the latest technology node, is about 1,000 times more than what it used to be 30 years ago. It used to be a couple of $1 million. Now it's a couple of $1 billion. That is inflation. But what you guys did, thanks to a lot of innovation, including, of course, improving the efficiency of the fabs, increasing the size of the wafers, and improving the entire throughput of the fab, you brought the efficiency to the point that it's 1,000 times more efficient. So you end up with the fact that almost the real estate of the silicon would be the same price that it used to be. Now, on top of that, you add scaling, and you see the phenomena is going to be staggering. So thanks to Dr. Moore's observation and insight and foresight, we took that foresight and proclaimed it as a law. And it became a self-fulfilling prophecy because now we wanted to be law-abiding citizens. And we tried to innovate in every dimension to keep that trend going. And in this chart, as you can see, the culmination of so many innovations on the device, on lithography, on manufacturing, on circuits, and everything comes together that you can keep this train going. But obviously, the bubbles are getting more dispersed and far in between as you move to the right, which is expected. So it's served us well, and it will be serving us in many dimensions, but it's going to be one of many exponential trends that defines our future. So I'm going to talk a little bit about fascination with exponentials in our field. We have been blessed by all these exponentials, but fortunately, the applications are growing a lot faster than all the innovations that we are doing. The demand for more data, mobile data is doubling every 16 months at least, and most of it is video. But on the other hand, bandwidth efficiency, the performance of our circuits, and the scaling of transistors are not getting as efficient or as at the same kind of rate as we saw we see in the applications that are driving our industry. And last but not least, battery energy efficiency is one of the slowest in terms of improvement. Of course, over the last couple of years, we have seen some changes. The trend is getting a little bit faster, but it's still a lot slower than the rate of the increase in data, big data, and expectations on new applications. So obviously, there is a growing gap, and it requires more innovation from this community to drive these trends more aggressively so that we can keep up with the demand and with the technologies that are creating the foundation for those demands. So as far as the areas that have not been chasing the scaling trend as closely, I'm going to talk about three main areas: analog, power, and MEMS. And I'll show that how these three areas have their own scaling trends and their own time constants for many reasons, and how the combination of these trends together can create a lot of more exciting opportunities down the road. So let's start with analog. I remember from days of the graduate school when I took the analog course with Professor Paul Gray, maybe he's here somewhere in the audience. It's a lot of exciting stuff on analog design, but there was a big trend that everything, all the signal processing is going to be digital in the future. Some people even stuck the A to D right next to the antenna. I said, doesn't matter how many blockers and out of band you have, just get them in, and then later we process it and clean it up. Fortunately, we come to our senses and said that's not the best trade-off that we are doing. And the reason is that for simple. We are living in an analog world. Unless you're watching Matrix movie that bits are flying around, what you're seeing is analog. What you're hearing is analog, what you're smelling is analog, and what you're transmitting or receiving in digital communication still is analog. We call it digital communication. So obviously, to interface with the world around us, we have to deal with these signals. And trying to push everything one direction or the other may not be the optimum case. Look at how our body works. The most exciting analog machine I can think of ever is our brain. Look at how it works. It doesn't digitize signals right after it hits your ears or your eyes or your nose. It does a lot of processing before and after to optimize the power. And maybe that's why our brain, with about 8 watt to 20 watt power consumption, depends on how deep you think or you're falling asleep now. I mean, depending on the power that you're using, you can do the same amount of signal processing that a machine with 1,000 times more power consumption today with the latest 7 nanometer technology is doing. So why is that? Maybe over 1 million years of evolution or creation, I don't know if it's creationist or evolutionist, whatever we call it, the system got so optimized that you really transfer and process signal as needed at the right point. So you don't put the A to D next to the antenna. You put it at the right place where it makes sense and drive the most efficiency. So what are the considerations? Everybody likes smaller. In our field, other than display and solar cells, the smaller is the better, right? I mean, displays are going the other way. But die size matters, cost matters, so of course we wanted to take advantage of scaling. But cost of migration to the next node is not trivial. It's almost redesigning, especially if you have unique features in your process. If you have optimized your process to drive some performances, you cannot just take the same design and kind of like carbon copy on the next node. Of course, as you shift to these finer nodes, you are going to get hit by signal-to-noise ratio challenges, mismatches, and potentially nonlinearities and leakages. Of course, this community of designers managed over many years to come up with creative ways to facilitate technologies to mitigate some of these. But the point is that migration to the next node has to make sense. Otherwise, it creates more challenges unnecessarily. What are the options while you are sitting on a node? You can get the architecture to the next generation by innovative partitioning. You can come up with many digital assist techniques that really make up for some of these mismatch and nonlinearity issues in the system. You can look at some of the mix and matches of multiple technologies. How about your front end could be a bipolar and your back end is a CMOS, as long as you can make SIP affordable and price competitive. So if you look at the trend of the dollars per millimeter square in analog, it has its own trend. A lot slower than pure digital, obviously. About 10% per year improvement in cost. So to just justify the cost of porting a design to the next node, you have to wait quite a bit. And that's why a typical analog node lives for about 5 years and sometimes 10 years. Interestingly, one of our most successful designs, which is really having a lot of demand in market, is about 20 years old design, and the technology that is 130 nanometer. And it's going strong. So my point is that really moving to the next node has to be justified by more than just scaling the transistor. And that nonlinearity you see on quarter micron is due to wafer size going to 12-inch that really creates another dimension of cost saving. But obviously, there is no rush to drive the next node. Obviously, in SoC, the story is slightly different because you are going to the next node not by choice, but by the force of digital. You have to offer a solution with massive number of gates on digital, and analog gets pulled in. It's like when you travel, it doesn't matter if you're in first class or economy, the flight time is going to be the same, right? So you're stuck with the same group of people. So it's kind of like you're dragged into the next node because the rest of the crowd is going to the next node. A lot of our studies shows that about 28 nanometer, you see the vanishing or diminishing value of the scaling in analog. Again, you may get pushed into that because of the digital side, but typically that is where you don't want to get too aggressive on the scaling anymore. Here's an example. As you know, radar is becoming really hot topic, and the reason for that is vision for autonomous vehicles, for drones, for robotics is becoming critical, and radar is a big part of vision in addition to ultrasonic as well as LiDAR and even magnetic sensing. But the fact that every car almost is going to have a radar system is critical. So there are multiple options when you design a radar chip, especially for new robotics and autonomous vehicles. You can go really fancy, use 3-5 materials on the front end to get the best gain and linearity on the PA side and best noise figure on the receive. And then use the CMOS for the back end. Or use SiGe, silicon germanium, which can give you a better performance in terms of noise figure. But the cost would be higher because obviously now you're talking about MCM and you need to get creative on SiP and MCM. So another option is that rather than scaling the whole system further down to a very deep submicron, how about we settle for around 40 nanometer, or maybe in the future 28, but still that jury is out on that one. And you get the performance that is almost matching silicon germanium because of the custom design in the process, not scaling. And one example of that, drain extended MOS, and using the back end from the synthesizer on, and the A to D is on CMOS, but the front end, you use these special transistors that really improves the noise figure and the power that you can transmit with these devices. So extensive analysis showed that going from 40 to 28, very little benefit unless you are dealing with the FT issues. But considering the fact that you need to cover very long range, 40 was the optimum. So the clear message here is that we cannot just follow the trend blindly, but we need to optimize the device to offer the best performance. We were testing this radar chip, and one thing was amazing. You can detect the breathing pattern of the people, that millimeter change of the variation in the distance with high accuracy. So it's not just automotive that is going to benefit from that, but medical. Same thing for security, and 5G, of course, is one of the other drivers of the next growth in the market, one of many, and that also can benefit from the same approach on the front-end design. Of course, most likely when it comes to base station, gallium nitride as a PA is the dominant choice because of the fact that linearity and performance requirements cannot be achieved by integrated solution, and also other sensing applications. Second one, I mentioned earlier that medical or personalized medicine is becoming a reality now. It's been a hype for many years, but didn't translate to real market. And the reason for that is the complexity of regulation. Unless you use it for just recreational, you don't need the clinical performance or FDA approved. But in this case, I'm talking about things that are prescribed by your doctor, not that you can go and buy it from a superstore by yourself. We see it's picking up. The latest one that is really exciting, and in Europe and lately in the US is picking up, is the glucose metering. The one that can report the glucose index of the humans in every couple of minutes to your phone and sending it to your doctor's office. That is a great example of disposable high-performance silicon, because disposable and high-performance go against each other. How do we achieve that? Technology like adaptive sampling, because in biosensing, as you know, because of the high ratio of FT over the bandwidth of the signal, you can get really creative on your signal processing. Using a memory technology that can withstand gamma radiation for a lot of sterilizations, and offering some fast wake-up radio so that it can have a disposable battery for a couple of weeks, coming together and making it reality. And now we see that a lot of personalized medicine applications are benefiting from the innovations in semiconductor industry. And this thing is a relatively small chip. It doesn't need the latest node of technology, but it's a combination of multiple innovations coming together to drive these kind of new applications. So in the continuation of the analog scaling, I'm going to talk briefly about data converters. Of course, that is the interface between analog world and digital, and a tremendous part of innovations and ideas and papers in ISSCC is around that. I borrowed these slides from Boris, showing a typical healthy doubling performance every 4 years based on a typical figure of merits, bandwidth times 2 to the power of ENOP. But interestingly, this chart shows that as you go to further, deeper submicron technologies, the benefits are not as great and diminishing for the reason that you are now limited by other factors, including the jitter in your clock. And the jitter is going to be the defining factor. That's why the curve starts dropping quite a bit when you go beyond 60 and 40. So let's talk about power. Power, again, when we were students, we thought all the power problems are solved. Who's going to work research on power? And it looked like that. A lot of top schools dropped their power courses because the problem is done, finished. Power is coming back with a lot of power. And who's out there not loving power? Anybody here? Anyway, so power is hot because things are getting smarter, more efficient, and they are showing up in places that we didn't even think of, smart power management. Power traditionally has not been a beneficiary of scaling unless it had to go with the rest of the train. In fact, the higher the voltage is, the more challenge you have when you want to scale the device, because most of the chip is taken by the power devices, and it's about optimizing the LDMOS, for example, rather than going to the next node. And as part of this trend, we see that, for example, in 20-volt applications with LDMOS, we see about 20% per year reduction in terms of the performance, improvement in performance in the reduction in RSP. And when you go to higher voltage, 50 volt, we see the trend is getting even slower, 14%. And as I said earlier, when you get to higher voltage, things are getting in hundreds and beyond. Scaling is not going to help as much at all, and that's why we see that it's not happening. But there are some very promising technologies out there, because we think always, if there is no scaling, then what else? Here is what else that we have been looking for. New devices. Now you see that gallium nitride or silicon carbide or some of these 3,5 materials really making up for scaling in CMOS only. Look at this chart. So the lower left means the highest performance. So when we go to 40 volt, GaN is outperforming silicon in terms of figure of merits. In this case is RDS on and gate charge. When we go to 100 volt, we see even higher improvement, 5.5 times reduction in R on and gate charge. But interestingly, when we go to 200 volt, the benefit is less. Because now the silicon guys managed to do some vertical structures, superjunctions, to get closer to GaN. And that shows that really you need to get creative with the structure of device and not just scaling. But when you go to 600 volts and beyond, and you see that GaN and silicon carbide start dominating again. So here's an example of a piece of technology which is inherently required. If you look at new advanced measurement devices, you see that the entire digital is shrinking, and all of the system is becoming almost power. So power blocks almost staying the same, and the rest of the system shrinking. And with these opportunities, we have a chance to go to the next stage of miniaturization by offering new devices and new technologies. So here is an interesting example of how GaN or a new power device can change the picture. Remember in RF, and we have a lot of RF experts in the crowd, there was the super heterodyne and homodyne, and then direct conversion to low IF or zero IF became very hot. I think in power, the same thing is happening. Look at this. This is a power conversion stage for a data center. Going from AC to DC 400 volt, then intermediate voltage with resonant converter, then go to 12 volt and point of load. In the future, we see that like what happened in RF, direct conversion, you can take it from very high DC almost all the way to a point of load. Obviously, if you rely only on a silicon devices, then you tend to get a hit on efficiency. But by running these devices at higher frequency and not compromising the performance, you can come up with really creative devices. So you can call it direct conversion in power. And these are innovations that are, I call it multidimensional, not just relying on wait until the next node solves all your problems. That's one of your tools in the toolbox, not the only one. MEMS. MEMS used to be just an external piece of our circuits. We interface to MEMS and we create some fancy circuits to drive or read the MEMS. I think it's going to be a lot more than that. One of the favorite MEMS that I have been working on and looking into, of course, is DLP, Digital Light Processor, which has about every 5 years getting almost twice improvement in the pitch. And today we have about 8 million meters on a single chip. So what do we do with this? Of course, projectors and all these projection applications are a big beneficiary. But you can get a lot more creative when you have more tools in your toolbox. And here is an example. This one is clear. For those of you who have followed GPS to get to this place, when it says next turn, you don't know if it's the immediate next turn or another 100 feet. Wouldn't it be nice to have all the arrows projected on the road so that you can see exactly what you're doing? But that is the past. Something more interesting that we did and quite exciting and seems to be working is that when you have this night vision problem in a rainy condition, it doesn't happen very frequently in California, but something we had to do with this conference. We're getting a lot more rain than typical. So the problem is that light gets reflected by the drops of the water, and you have impaired vision during this driving, which is very dangerous. So we put one of these MEMS devices in the headlight. Rather than one beam, we created 64,000 beams. And we detected where the raindrop is and deflected the light around the raindrop. Look at how it looked like. So we get the location of every drop, because every drop matters, as I said. We detected every drop as it's coming and deflect the light around that so that it's a lot cleaner. Of course, we haven't tested it in the Florida storm, but in California it's working, so we'll see how it works for the rest of the world. Applications are abound when you have more tools in your toolbox. These days in the news, we are hearing real news, fake news, and it's confusing. So we technologists came up with another term, augmented reality. It means that it's somewhere between reality and non-reality, whatever we call it. And we put that DLP to project that 3D image in front of you, hologram, spectroscopy, and so on. Another aspect of MEMS, which is really fascinating and is coming up as another tool in the toolbox of scaling, is MEMS resonators. MEMS resonators are very exciting because they can be integrated as part of your circuit as an integrated clock reference with very high performance phase noise, Could be a programmable filter. Typical phone or base station today is covering several standards and tens of frequencies, and you need multiple filters. And having a programmable, tunable filter is a blessing for a lot of these applications. Frequency hopping techniques using a MEMS resonator. Even some people have gotten more creative and working on encryption using the array of resonators. So resonators are becoming part of the circuit, and it's growing. The rate of the growth in terms of performance, depending on capacity versus piezo, is different. Piezo tend to be slower because you need to spouter or electroplate or some other PZT or aluminum nitride, whereas capacitive is less material intensive, so you see that the growth is much faster and much more promising. It's becoming reality performance-wise, power-wise, and by the way, if you have a resonator that is oscillating at gigahertz, then you don't need a PLL necessarily. So you can wake it up and it's on. And that creates a unique opportunity for IoT or other applications that are highly intermittent in terms of the transmission. I know that I'm a bit over time, but bear with me for a few more minutes. So what were the unintended consequences of single dimension scaling? Any problem that you hit in your design, you say, wait for a couple of years, next node is going to fix it. That story is no longer valid. You need to get more creative on the same node and look at other opportunities and still benefit from next node when it comes, but don't put all the bets on one trend. Non-digital circuits had to comply with the digital intensive circuits going to the next node. And again, it's exciting because it brings the new challenges in the design, but sometimes there are trade-offs in the performance that need to be aware of. And limited number of applications require such a huge scale of tens of thousands of wafers a month in 7 nanometer or beyond. And this chart is kind of interesting, showing that 3 elements: fab cost, process development cost, and later I'm going to talk about design cost. Fab cost and the process design is going up so quickly that number of players who manage to do these kind of things are shrinking from 22 to 4 only, or maybe 3 very soon. And it's not just the fab cost and development cost, but the design cost. So this chart is kind of interesting, showing the design cost and the number of IPs in a typical big SoC. 190 or 200 IPs. And we are dealing with top designers in the world here. You know that when number of IPs grows, the chance of hitting first silicon success shrinks quite a bit. So huge cost, and only justified for markets that are highly large volume, like a mobile market and some other markets like GPUs and CPUs and DSPs, but not every market can bet on that. So what are the other headwinds for us in circuit and system community? Fortunately or unfortunately, a lot of value is shifted to applications, to software, and to services. People are excited about putting very small amount of money, come up with a new application and count the number of hits, and that defines your business plan. You cannot do that in semiconductor easily. No matter how many billions of transistors, how many ICs you have, people expect flawless execution. If they see a hiccup in the phone, they throw it away and go to the store and get another phone. So it's kind of like we spoiled ourselves by having such a flawless execution of billions of transistors. And as a result of that, we see a fewer number of startups in semiconductor. People see that the investment and the patience for a semiconductor startup is higher and longer, and that is not good because a lot of innovations depends on this ecosystem of startups and big companies working together. So we need more exponentials. What are those exponentials? Obviously, the scaling, as Cliff mentioned, it keeps going. We need that for many applications, and it's very critical for this big data. But also, there are dimensions that need to be added, and amazingly, a large number of IPs, from lithography to new materials, new devices, and new packaging techniques. Heterogeneous packaging could create a new wave of future. So what I mean by multidimensional innovation is device, packaging, interconnect, because you need to have advanced interconnect to facilitate SiP at low cost, system partitioning all come together, and maybe none of them by itself is exponential, but we know from Math 101 there are multiple ways to create exponential. You can add multiple nonlinear improvements, and when we sum it up, it approximately will be exponential. So I would like to conclude my talk with a brief summary. Past 20 years, we have been blessed by single major trend, in many cases single market, and single set of applications. Next 20 years is going to be even more exciting. Differentiating technologies, many different markets and applications, and many players to drive the next exponential. Thank you for your attention.